Okay, good morning everyone, or good afternoon, depending on where you are. It's time for the webinar to start. So welcome to the introduction to the energy transition, which is definitely a topical subject at the moment, which impacts all of our lives. I'll just do a quick introduction to the webinar and then hand you over to Gijs Holstege, who's going to be delivering his presentation. Gijs has got over 31 years experience in the oil and gas industry, and he's got experience in technical leadership roles, so he's got a good understanding of what's going on and what's been happening in this area. I'm the director of Esanda. We're an upstream oil and gas training company, and we're all for the energy transition, despite being oil and gas dinosaurs ourselves. And we've been running this webinar series since late last year, and it's been very successful as well as today. We've got over 200 registrants. I'm not sure how many people will turn up. We tend to get about 20-30% of that number. So I'm just letting people in as we speak. And our next webinar is coming up next week, actually, is SURF, Subsea Umbilicals, Risers and Flowlines, the role of sealing on the distribution of trapped oil and gas, a little bit more technical, and gas well performance, keeping it simple. We have run some other energy transition webinars earlier in the year, which are all on our YouTube page, as this one will be. We're recording the session, and we will upload it to YouTube in the next day or so. And we won't take any questions during the, we won't take any questions with Gijs, but anything I can answer during the session, you can send your questions through in the chat. And anything I can't answer, we'll pass on to Gijs at the end of the presentation. We do have some, if anybody's interested in talking about training, you can contact me by email, or you can take a snapshot of this QR code, all the modern technology, or arrange a booking with this link through a Zoom meeting. Okay. The rules for the webinar will have you all muted. Questions will be through the chat function. You can send your chat questions through during the session, and we will try and answer all the questions before we close the session, but we will take emails after the session if anyone's got anything they think of afterwards or don't get a chance to get it answered during the session. As mentioned, the session's being recorded, and you'll be able to access the recording on our YouTube channel. We'll send the links out when it's ready. And any further questions on this or any other topics you might be interested in, just email us at training@esandaengineering.com. Okay. Now I'll hand over to Gijs to do a quick introduction to himself and also to present his material. Okay. So you're welcome to share your screen, Gijs, or do a quick introduction now that you're there. Yeah, all right.
I'll share first of all.
Sure. Okay.
Okay, so the very first question I have to you all is, can you see my slide, which is a beautiful picture of the rainforest in Brunei, which is the country where I was last working for Shell? That's one. And can you hear me? That's the other question.
I can hear you, Gijs, and see your presentation. It's all looking good.
Excellent. Okay, all right. So I'll continue then. So, yeah. Good morning, good day, everybody. I'm not sure in which time zones everybody is at, but I am currently presenting this from the Netherlands, in The Hague. And as I said, I just really like this picture because I spent 4 years working in Brunei, where I was exploration manager for Brunei Shell Petroleum, looking for new oil and gas. And that sounds, of course, very contradictory to the topic I'm about to present. So let me first talk a little bit more about myself and why I'm doing this. So this is kind of a picture that I guess symbolizes my own energy transition path, personal energy transition. On the right-hand side, you can see a very high-level CV of what I've been doing. On the left is kind of where my interest in energy transition has started to come into play. So I joined Shell from after I graduated as a geophysicist in 1990. And I was immediately very fortunate to go abroad and work in a couple of countries. Mentioned there, United Kingdom for 4 years. I was in New Zealand for 6 years, where my first 2 children were also born, my oldest 2. Then I went to Thailand for 2 years, where my 3rd child was born. And then I spent 4 years in Syria, in Damascus, up until 2006. And then 2006 to 2012, I worked in Saudi Arabia 6 years, which I thoroughly enjoyed. And there, for the first time, my interest in carbon and CO2 was really triggered because we were trying to develop a sour gas field, which created a lot of byproducts such as CO2 and sulfur, and we need to find solutions for those. And that project, in the end, never materialized. It was a big project, but it was just too expensive. But the interest in trying to find solutions for large amounts of CO2, that stood with me. I was then back in the Netherlands for 4 years in a corporate role, doing business planning for Shell's global exploration function. And there I had access to pretty much all of Shell's data, planning data and forecasting. And I started looking at, for example, the CO2 forecasts that come with the operations that we do, and developing an interest around that, and having really good conversations around, okay, how do we manage all this? And, sort of sitting there for 4 years at the corporate headquarters, understanding how decisions and strategy are made. That was all very interesting. Then I returned back to a technical function, which was my last role in Brunei for 4 years. And there's a whole list of things there on the left, which I got involved in. I was responsible for generating or managing a whole bunch of environmental initiatives that were coming in through a funnel from various individuals, and trying to help support those into implementation. Part of the energy transition strategy for Brunei in the informal capacity. We had some nature-based solutions, which you'll hear more about later. And now I left the company in 2020, and I'm now basically really focusing 100% on sustainability and energy transition. And for me, it is a complex subject. There's a lot of urgency required. And the complexity is something that I think really needs to be explained if people understand why we are going through an energy transition. We can't change our behavior. So for me, I have a real passion around educating on this topic, and that's why I'm really doing this training. And you're welcome to afterwards have a look at what is on offer through Esanda, because this is only an introduction, and there's a lot more behind this. It's a very broad topic, of course, and I will therefore necessarily only touch on a few things and miss out a couple as well. So that's enough about me. So as I said, it's arguably one of the biggest challenges of our time. We have already increased our temperature up to about 1.2 degrees on average in the globe since pre-industrial times, and we are feeling the effects, of course, already. Our CO2 concentration in the atmosphere has risen from 280 pre-industrial concentration parts per million to currently about 415 parts per million, which is causing this rise in temperature. 2/3 of the total greenhouse gas emissions are really from energy activities, and of course any human activity requires energy. So we'll talk a lot about that. That's the biggest part of the, let's say, challenge as to how do we decarbonize our global energy system, and that's what we call the energy transition. Sorry, I just need to change one thing on my screen because it's okay. That's better. So now I changed the title of this slide to societal awareness is changing. I think it actually has changed. I mean, this slide I made this last year, and the amount of coverage now in the media on anything related to energy, to climate change, is actually encouragingly, large. I mean, you cannot ignore this issue anymore, and that has not always been the case. Of course, that's really happened in the last year or two, as far as I'm concerned. So, in some ways, I feel almost this is redundant, this course, because you may already know a lot of what I'm about to talk about. But in any case, there is urgency, and it's important that we all have a broad understanding of the science and the facts behind it. So what I will talk about, I'll split it into 3 parts. We're going to talk about, okay, is there a problem? And maybe that's no longer necessary, but I do think it's still important we just understand some of the basics behind the climate science that is used throughout all of this global discussion. throughout Paris and the UN and the IPCC. That's going to be a bit of a depressing story, as you probably can imagine, because we do have a problem and it's not good. Then I want to spend a third of the time on, okay, what are we going to do to solve it? That's really very much the heart of energy transition. And then finally, a third part on some enablers and key technologies that can help us there. So first of all, one of the common critiques that is heard in the past in climate change debate is that, well, climate is always changing. Global warming, climate change is part of a natural process. So really, how unusual are these changes we are seeing today? And is it really a problem? So if we go to the longest timescales, the geological timescales, you can see this picture in the middle on the vertical axis. It goes back 600 million years. If I take out a part which we call, as geologists, the Cretaceous, that's about 100 million years ago. That's a kind of little cartoon of what it may have looked like. Dinosaurs around the planet. Atmospheric CO2 levels were several times higher than they were today. There was no ice on the face of the Earth, and global temperatures were much higher than they are today. And you can see that on the graph in the middle of the slide. The blue line is temperature, with the axis on the top, and the black line is the CO2 concentration with the axis below. And you can see that these periods of high global temperatures coincide with significantly higher carbon dioxide concentrations in the atmosphere. In fact, concentrations, getting into the 3,000 to 4,000 ppm, which are essentially toxic for humans. Now photosynthesis has extracted huge amounts of this carbon from the atmosphere and buried most of that carbon beneath the Earth's surface over the course of these hundreds and millions of years. And we've only just appeared on the planet in the last 3 million years as a human species, and that is the line, the very thin line at the top there. So you can see that the conditions we now have on the planet are quite unusual. It's generally been much hotter. And by burning fossil fuels, we've taken a lot of that carbon that nature has buried over that time period and put it back into the atmosphere over a time frame of only 100 to 130 years or so, 1 million times faster. So what's really relevant is not the magnitude of the changes, but it's the pace of the changes over 100 years, 1 million times faster than what nature has actually been able to store. And that's likely to exceed adaptive capacity of living things, which includes us. Now, the other thing is, what's interesting, there are 5 extinction events in geological history, and the most recent one is probably the best known. That's when the dinosaurs became extinct, which is about 65 million years ago. But the biggest mass extinction event, however, is during the Permian, and you can see on the graph the Permian there is about 250 million years ago. That's when 95% of all known species disappeared. Now that you can see there is a big jump up in temperature and in CO2, and it's thought that is caused by a period of intense volcanic activity. So a lot of CO2 gets released through volcanoes, including also aerosols, which have a temporary cooling effect. But over time, it's the CO2 that really controls much higher atmospheric temperatures. And there's a whole bunch of other events that I can talk about, which where you can see that the CO2 and temperature are very, very closely related. So yes, climate has had larger changes than we are currently experiencing today, but those changes have generally taken place over 10 to 100 millions of years, rather than a few decades as we are currently experiencing. So the issue is really the pace of change and how we can adapt to it. And another way to look at this, I just love this visual, which I took from a podcast I'm currently following by Nate Hagens. And it's, you can think of fossil fuels as we've had this luxury of a battery that's been charged over this 600 million years or so, this photosynthesis battery of stored solar energy. And then a bunch of mildly clever, highly social apes broke into the cookie jar of solar stocks, solar energy stocks. And we've been having this party for the last 150 years and basically created the world as we know it today. This carbon pulse, if you want to call it that, has allowed the work equivalent of about 500 billion humans to be done, which has created, all the wonderful society as we know it today with all our gadgets and our inventions and machines, etc. But already very early on, there was actually, it is known that CO2, burning fossil fuels, does create a bit of an issue. here's a little newspaper snipping from a little known newspaper in New Zealand called the the Waitemata and Kaipara Gazette in 1912, so 110 years ago. And it already talks about the furnaces of the world are now burning about 2 million tons of 2,000 million tons of coal a year, and making this link to CO2. So this impact was already known. It's not new. But I think this fossil fuel system that we've been benefiting from, it's an exceptional energy system. We will not have something as efficient in terms of energy density per liter or per kilogram of material ever again. This fossil fuel was a unique, and we really need to transform that energy system to a non-fossil system as we reach the limits of warming in our planet. But that's not going to be straightforward. And the question that is out there really is, can we actually even maintain the level of the total capacity of energy system that we currently have built through the use of fossil fuels, and do we not need to reduce? So what I want to leave you with is a slogan of, it's not just about using different energy forms, but it's also about using energy differently. So let's talk about temperature. And I know this is probably no longer news to most people, but these besides these CO2 measurements, we have about a century of widespread measurements from around the globe, and these are thermometer records from land-based stations and islands, and shipboard measurements of ocean surface temperatures. And they provide us with more than a century of reasonably global estimates of surface temperature changes. And you can see this animation here as we cycle through the years, how that changes. You can look at the color scale up in the top left there. There's lots of variation there in the global temperature. So we talk about an average temperature increase, but you can see that over the globe, there's lots of variation. Let me just click on that again and see if I can run that again. We expect more warming at the higher latitudes as ice melts, and then you lose that reflectivity of ice. This ice albedo feedback effect kicks in, which is what we call. And that adds to the warming there. And you can see also that land masses generally warm more than oceans, which are slower to warm. So global temperatures have indeed increased over time. The Earth has warmed about 1 degree Celsius, a little more than 1 degree Celsius since the mid-19th century, as far back as the surface temperature observations go. And can we talk about CO2 being the cause of that? So I just want to take you through this slide because it's actually a very good piece of evidence, that, for example, the warming we are seeing is really human-induced. Modern day climate change appears to be anomalous without any obvious precedent in historical past, the pace. But that alone doesn't establish that this is caused by human impacts. But using climate models, we can address that issue of causality very clearly. You can see in the models here on the right-hand side, the observations are the lines in black, and these are the temperature observations and measurements. So these are the facts, let's say. And if the climate scientists run their models, but they do not include the human-induced CO2 into those models, into the atmosphere, they cannot really match what is happening with respect to the observations. And that is represented at the bottom right by the graph saying only natural forcing. But if we include all the CO2 from the fossil fuels we have been using, that matches all very well. So that kind of tells you already, okay, this is related to human activities. If I look on the left, it looks a rather busy little graph on the left, but the key thing here is that you see 4 temperature charts again, and all of them show temperature increasing over time. I know you can't read the axis, it's too small, but this is the temperature increasing over time in the part of the atmosphere we call the troposphere. But the exception is the one on the top. There you see temperature decreasing with time. And these are temperature measurements taken in the stratosphere. So the troposphere is really where our weather all happens. This is where the air is the densest, and this is really, for us, the most relevant part of the atmosphere. Once you get to the stratosphere, about 16 kilometers or so, that's a much thinner part of the atmosphere. And the greenhouse gases, they sit just below that in the troposphere. So this really shows that if for example, the warming would have been caused by solar radiance, an increase in solar radiance. Well, we would also see that temperature increasing in the stratosphere, and we do not see that. We see it decreasing, and that's because it's a net sum zero gain. The Earth is warming up because of the greenhouse effect, but there's no more solar radiance hitting Earth, so that somehow needs to be compensated, and that's what we see by the cooling of the lower stratosphere. So there's very clear indications that this is all human-induced. Yeah, more bad news, of course. I put this slide together last year, but equally, I could have made a similar slide for this year as we are experiencing. For those of you in Europe, you know that we've just gone through quite a few weeks of, quite nice hot weather. I mean, for me, I haven't suffered too much from it, but we see river levels falling low, water levels low. We see droughts happening. Certainly in Southern Europe, it's been exceedingly hot, and that's causing all kinds of problems. But equally in the United States, there are droughts and heat waves happening, and then you get sudden downpours, which, of course, as the atmosphere warms up, it can hold more moisture, so precipitation events become more extreme, and that's what we get when you see the flooding, for example, in China last year, or even in my own neighborhood in Europe. In south of Holland last year, causing all kinds of problems. We're not used to having these flooding events in the middle of summer. We usually have them kind of in spring when the ice from the Alps melts. So lots of things happening here. If you look at the IPCC reports, they have done an extensive job of mapping all the different impacts that climate change is already happening, and we can see these adverse effects on human systems, in terms of water scarcity and food production, impacts on health and well-being, and cities, settlements, and infrastructure. So this is quite a nice chart which maps it all out. You can see, whatever region you happen to be in, you can have a look here and you can see what is happening. The plus means it's having a good effect. There's not many of those. There is a plus minus where it's kind of, there are good and negative effects, but there's clear areas where it's a very adverse effect, which is represented by the minus sign, with the color being the level of confidence. So you can see, for example, in Europe, if I just pick that out, in terms of water scarcity, Northern Europe is getting quite a lot of extra rainfall, but Southern Europe, that's where it's becoming a lot drier. So there's depending on the location, there's different impacts, but overall, human systems are being impacted. Just one or two still bad news slides. This one is a picture that I picked up from The Economist, and they really had a good article that showed, what areas of the world become uninhabitable, and why is this boundary 1.5 degrees Celsius rather than 2 degrees Celsius so important? The percentage of the world's population that would be exposed to extreme heat waves once every 5 years, it jumps to 37%. In a 2-degree warming world, compared to only 14% if that global temperature were to remain at 1.5 increase. And that's why Paris Accord is so important. But equally on biodiversity, dramatic increase of loss of biodiversity or species moving to higher, cooler latitudes. That basically doubles when you go from 1.5 degrees to 2 degrees Celsius. Coral reefs, declining global fisheries, all of them have, it's not a proportional change, it's quite a dramatic change from 1.5 to 2 degrees. And beyond 2 degrees, there's lots of tipping points that we expect will cause irreversible climate change. And if you think, well, I'm sitting there in the Netherlands, so not really a problem for me. Well, actually, what this doesn't show is sea level rise. Of course, we live under sea level, and I think there's 10% of the world's population live within 10 meters of this current today sea level, so they're very vulnerable to sea level rise. Now, just very briefly, I talked a little bit about the IPCC. They do a very good job of bringing together all of the world climate science. So the IPCC itself does not do scientific research, but they bring together all of the world's climate science work, and they, synthesize that into these reports that they publish. And here is the latest kind of set of models that they run, and you can see the past millions and thousands of years. They match very nicely with the pictures I showed before in terms of temperature change and CO2. And then they have these projections to the future. And the acronym SSP stands for Shared Socio-Economic Pathways. So these combine the climate change with also scenarios about human society and the decisions that we will take. And depending on how we deal with this, and you can see 2020 as the dashed line there, that's where we currently are in terms of CO2 and temperature. We can, radically reduce our emissions, and then we are in this SSP1 2.6, and that number stands for the radiative forcing, or that is essentially how the greenhouse effect is characterized, and that's a number of watts per square meter of radiation that is returned back to Earth on top of the solar radiation. Or it can go horribly wrong, and we are ending up on this curve here, SSP5 8.5, shown in this very, very red hot picture. Currently, the blue arrows that I have in the picture, they point to this scenario of SSP2 4.5. So that is what we currently seem to be on in terms of a trend. So a stabilization of emissions, but not really a reduction as we need. So we are not there yet. These pictures, by the way, you can access them all through the IPCC website. They have a very good interactive atlas, and you can look at any region in the world, see what this particular model means for your region in terms of heat or precipitation. It's very important to address this issue of climate CO2 budget, and that's what I'm trying to do on this slide. You can see there's a linear relation here between cumulative emitted CO2, the axis on the horizontal, and temperature, which is the axis on the vertical. And the current pathway we're on, I already mentioned, SSP2 4.5. That line basically means that by this, this is up until 2050. This intersects a 1.9 degrees Celsius point at the axis here. And by the time we've emitted the CO2 we expect under that scenario, and of course, what we really need is we want to stay at 1.5 degrees, and that means that we cannot go over this additional 500 gigatons of CO2 we have as our remaining budget. So when you hear the terms CO2 budget, this is really what it means. Up until 2020, we have emitted about 2,500 gigatons extra CO2 into the atmosphere, and if we are to remain within the 1.5 degree warming world, we cannot emit more than another 500 gigatons. So keep that number in mind, 500 gigatons. Now we get into really, okay, so where are these gigatons all coming from? And the pie chart in the middle shows that about 3/4 of emissions are coming from energy use, and energy can be used. Energy is used across a number of different sectors. There's energy use in industry, transport, and energy use in buildings. And so if you look at the chart beneath that, that really shows in terms of that 75%, which if you take, we emit in total about 50 gigatons a year. So that means with the budget I just explained to you, we have 10 remaining years left if we can continue emitting at the current levels. And the energy part of that is about 38 billion tons a year. And so that 38 tons a year, you can see on this chart, there's been a rapid growth in our emissions, as a result of the industrial revolution using fossil fuels. That growth initially was really through the countries, OECD countries such as Europe, the European countries, and North America. But these countries, they have been part of a drive to reduce emissions since Kyoto, and so they have been reducing, not enough, but to some degree. But of course, China has emerged as a big economic powerhouse, and India, of course, as well. And so they have been emitting CO2 as a result. Together, China, European Union, and the United States, they account for about half of our global emissions. So it's very important that these three, China, European Union, and the USA, that they really tackle their energy transition urgently. That will have a big impact. And the other message, of course, is because there's a 75% decarbonizing the energy sector is a critical element of meeting Paris. So, having given you all this bad news, how do we now go about solving this problem? Very briefly, the history, because there is one of the ways to resolve this is going to require unprecedented kind of global collaboration. And one of the good things that is happening, of course, and it's been happening for many decades, is this collaboration at a United Nations level. And so I want to give you a little bit of history here very briefly. On the chart on the right, if you look at the top here, you see something called FAR. That stands for the First Assessment Report. That was in 1990, and that really recognized for the first time that there was a problem. And that led to the UN General Assembly creating this framework convention, UN Framework Convention for Climate Change, UNFCCC. So there's a lot of acronyms, and I've given a couple of them on the left here on the slide. And that was really signed into force at the Rio Earth Summit in 1994. The countries that signed that treaty are known as parties, and parties meet annually at these conference of parties to negotiate multilateral responses to climate change. And this was quite remarkable at the time, because in 1994, when this took effect, there was much less scientific evidence than there is now. So the fact that this was created, I think, was remarkable. And today, this UNFCCC has near universal membership. It has 197 parties or countries. They have ratified the convention, and their goal is to prevent dangerous human interference with the climate system. That's the ultimate aim, by stabilizing greenhouse gas concentrations at a level that would prevent dangerous human-induced interference with the climate system. Importantly, this puts very much the onus on the developed countries to lead the way. The idea is that, of course, as developed countries, we have benefited mostly from this carbon pulse, this fossil fuel boom in terms of our economy. So we are the richest, and therefore should also bear most of the burden of solving it. These so-called Annex 1 countries, mostly the OECD countries, which included also 12 countries from economies in transition, they were expected by the year 2000 to reduce emissions from 1990 levels, and some have taken some strong action to do so and have succeeded. The very first conference of parties, this very first meeting in 1995, was hosted by Germany and Berlin, by Germany's environmental minister, then Angela Merkel, and that laid the groundwork for Kyoto. Now, Kyoto became quite a politicized protocol, but it does operationalize this UNFCCC by committing industrial countries and economies to transition to limit reduced greenhouse gas emissions. And you can argue how effective that has been. In the end, I think the US did not sign it. China also didn't agree to it. But overall, it's been kind of a success, because those OECD countries do now have about 24% lower emissions than in 1990. So that's a little bit of history, and there's lots of great reports that the IPCC have published over time, leading to what is currently the most up-to-date one, which is AR6, and that is Assessment Review number 6. And that really formed the basis for last year's COP26 and the upcoming Conference of Parties in Egypt, COP27, which is due to take place in November. Of course, Paris, you've all heard about, so I won't stay too long there. But the key thing about Paris was it was 2015, and it did bind all of the participants to submit ambitions in the form of what are called national determined contributions. So every party, every country that signed up to this had to submit targets and ambitions and a plan how to reduce their individual emissions. And that is a little bit voluntary, but if that had not been the case, if it had been too prescriptive, I think probably many countries may not have agreed to this Paris Accord. But these NDCs are at the heart of the Paris Agreement, and we'll talk a little bit about those in a second. For example, the European Union, it has its Fit by 50. It has committed to reducing net domestic reduction of at least 55% in greenhouse gas emissions by 2030. So that's now 8 years away compared to 1990. So that's quite an ambitious one. And the idea is that these national determined contributions, they're kind of a ratchet mechanism. So the first ones that were submitted were nowhere near enough. There was an update for some countries just prior to Glasgow COP26 last year. And at COP26, they agreed it's still not enough. So let's agree that we actually update them all within a year, and that's due to be done by this year, November at COP27. If you are interested to see how the different national determined contributions all compare, there's a great NGO that tracks all of these NDCs and analyzes them, studies them, and then makes a kind of a judgment whether they're sufficient or not. And you can see the color map here. You know, this is from the Climate Action Tracker, the CAT. You can go to the website. It's very, I find it very useful. And you can see that most of what is being submitted is not sufficient. In fact, there's only a few countries that are almost sufficient. And notably, I would say Australia, you know, it's highly insufficient. China was highly insufficient, India. So these are the ones that are really lagging behind. European Union and even US doing much better. Great Britain actually is almost sufficient. They have got a quite ambitious NDC. So that's a big, you know, a great role model to follow in that sense. But of course, a lot of the reasons why these are insufficient is because these pledges and these NDCs are easy to make in the longer term, but they need to be translated into policy, regulation, and rules and actually operationalized. And that's where the problem is. And that's a real political struggle in many countries, as we know. Now, the good news is that Australia has just got a new government and they are entering this new era on climate change. And in fact, only just this month have submitted an updated NDC. So I don't know what that color now will look like. I don't think they have had time yet to analyze it, but I expect that to change. That should be much, much better with this change in focus of the Australian government. And of course, the big news is, you know, President Biden finally managed to pass this massive package of ambitions into legislation in the US and sign this into law. So that is going to be a huge boost, and that I think will also alter the whether it's sufficient or not. The targets certainly are sufficient, but still a lot needs to happen. But at least now this is moving into legislation and policy, and the money has been committed to help US almost, I would say, lead the way. So, and it's a little bit unfortunate that China and US have had a fallout lately over geopolitical issues such as Taiwan and whatever else. But China and America at last year's COP26 really agreed to work together. And then you have, as I showed, 50% of emissions really covered through the US, China, and the European Union. So it's progress, but it's still probably not enough. And at the moment, you can see here the various pathways. If we take what we are currently on historically, there's this 50 gigatons, which is total emissions. And if we take all the policies in action, then the models show that we are on this pathway to about 2.5 to 2.9 degrees Celsius. Let's say on average, by the end of the century, if we continue doing what we're doing, we will have heated the planet 3 degrees on average, you know, globally. And that is, of course, a very untenable situation. This is going to cause too many problems. But what we want to be on is, of course, this pathway, which is consistent with 1.5 and brings us to net zero. And in this case, a little bit later, but by 2050, that's been a pledge many countries have made. And there's a bit of an ambition gap here at 2030 already. So it's quite a big ambition gap, but hopefully with this yearly COP now getting an increasingly urgency and governments really realizing, populations and citizens realizing how important it is, and the NDCs ratcheting up, becoming more ambitious, hopefully we do start moving in the right direction. But you can track all of this through this excellent website. It's very, very good. Okay, so further global context before we dive into the energy system itself. All of this change needs to happen in a world where the population continues to grow, and you can see that on this chart here, primarily driven by growth in the African population, so the third wedge from the bottom. Historically, our GDP has been growing at 3% a year, so there's a little blip here at 2019, that's caused by the corona pandemic. But if we take that 3% and continue it, then our economy basically doubles from where it is today by 2050. So you can see the size of the challenge. We need to, this economic growth we've been used to has been fueled by this fantastically easily available, cheap, high density energy source of fossil fuels. And we need to change that whole system if we want to remain within the boundaries of a planet, while at the same time, no one wants to change their lifestyle, you know. So it's So it's quite a challenge. And in fact, there's a lot of debate right now whether even that I don't believe we will grow GDP in the way that this curve is showing. I think that's something that is based on past growth, but there's more and more discussion happening within the macroeconomic community of, can we really, I mean, the planet can simply not afford to keep growing in this way. We're running up against so many different boundaries, ecological boundaries that we cannot pass. How can we decouple energy use from GDP? Can we, grow our welfare, but reduce our use or our reliance on energy to a degree? So there's a lot of debate about that. So I don't think it will happen this way, but it just gives you a sense of how big the challenge is. I put a little link at the bottom there to a podcast which dives into this very topic. So if you're interested in that, take a note of that. It's a great podcast articulating very well the dilemma we have with our current macroeconomic system. Okay, so let's talk about the energy system. And today's energy system is shown in this visual on the right-hand side. And as you expect, 79% of our total energy system is coming from fossil fuels today, about 79% from coal, oil, and gas. You can look and see that the total energy consumption is just under 400 exajoules. Units in this whole energy world are always a bit of an issue, but the exajoules written at the bottom there, that's 10 to the 18th joules, and that links again to terawatt hours. So there's a whole area there in my course, and we go into that a bit more to understand these units. The energy consumption, 400 exajoules a year. Renewables share currently, what's that in electricity, about only 25%. And this energy system, the fossil part of it, emits 75% of all our CO2. So that's what it looks like today. Where do we need to go? So that's the picture you've just seen with our 79% of fossil fuels. And this is a picture of what it needs to look like to meet the 1.5 degree scenario, to not exceed that. And I've taken this from a scenario from this organization called IRENA. This stands for the International Renewable Energy Association. And there's plenty of these roadmaps and scenarios from different institutions. There's the International Energy Agency, there's IRENA I just mentioned, various companies have their own. They differ in some respects, but they all kind of agree on the high level changes that are needed, which really is about more electrification and more renewables. So I'll have a look at this for a second as we go through some of the key changes. I'm hoping that the first thing you see is that the 2050 energy system, where we need to be, it is actually showing a slight reduction in our energy consumption. So there's a lot built in here around energy conservation, energy efficiency, and doing the same with less energy. So that's one important message. Fossil fuels reduced to, about 13% of the total energy mix. The electrification is a big component. Look at the change in the size of the electricity bucket there. In fact, if you include renewable electricity used to generate hydrogen, which is that arrow I've added, the plus 8%. So in total, electricity goes from 21% to about 60%. So it's a tripling of our total electric generation system globally. That is huge. And of that tripled electricity system, renewables grows ninefold. So it takes 90% of all electricity 2050 needs to come from renewables. There's also renewables in district heat. Nuclear energy has a role in there. Hydrogen, you can see it doesn't feature at the moment, but in the system of the future, it has a big role to play as a key energy carrier. And biomass is another thing that is increasing dramatically. Use of biomass, and that's seen as a kind of a net zero carbon solution, because you're burning stuff that has grown and taken up CO2 from the atmosphere, and by burning it, you can put it back there, but it's a net zero game. So it's a little bit controversial. You could also capture that and put it underground, which would take out the CO2 altogether. So, this is what the future energy system needs to look like. And that energy system, this is another way of looking at our emissions through what we call the 4 key energy emission sectors. And they are really about power generation, industry, buildings, and transport. So this is I love these diagrams. This is called a Sankey diagram. It shows the flow of where CO2 comes from. So on the supply side, of course, coal, gas, and oil. But on the demand side, there's energy provisions into things that we use, but there's also direct use of energy, and there's carbon products. But overall, it's really the power generation, industry, buildings, and transport where the decarbonization impacts need to happen. And of course, reducing demand for energy gives you a lot more flexibility in changing this picture. So we need rapid transitions in all energy sectors, and the one that transitions the fastest, as you can see on the chart on the left, is electricity. So electricity, of course, we're already seeing a lot of wind farms and solar farms impacting the electricity sector, and that just needs to get even more. And these are changes which are really unprecedented in terms of scale, but maybe not in terms of speed. But on the right, you can see the relative impacts. The main ones are being this drive towards more renewable electricity, the drive in energy conservation that takes, that can add up to or reduce our emissions by up to a quarter. Then there's electrification in end-use sectors that currently are not electrified. There's hydrogen and some others there at the bottom. So, yeah, these 4 sectors really decarbonize in different ways, and I'm going to briefly go through each one and talk about them a little bit. And the very first thing is the energy intensity of GDP. So this is the amount of energy per unit of GDP. That really needs to reduce 4% every year in order to make this kind of roadmap. So that's all about energy efficiency and making use of less energy. But equally, electric car sales, you can see between 2020 and 2030, that needs to increase by a factor 18, and capacity additions of renewable electricity, so globe, solar, and wind, that also, those capacity additions needs to increase by a factor 4, annual capacity additions up to almost 1,000 gigawatts per year. And 2020 saw just over 200. Now we are on a path of this increasing. I don't know what the numbers are for 2022, but it is moving in that direction. But it's going to be really this clean technology decade. And just to show you, here's a roadmap from the International Energy Agency. There's a lot of things that need to happen. I'll just highlight a few of them. You can see here in terms of coal plants, as of 2020, as a global, we cannot, we should not approve any more new unabated coal plants. I think that's kind of more or less happening, although recently with the war in Ukraine, you can see more coal plants now that should be mothballed, but starting up again. Another equally controversial one, no new oil and gas fields approved for development. Now, I know that's not happening. There are definitely new oil and gas fields being approved for development. But these are the very ambitious and urgent milestones that are required in order to meet the Paris Agreement. Here's another one, 2030, all new buildings to be zero carbon ready. And I'll talk a little bit about what that means. 60% of global car sales to be electric by 2030. And in fact, 2035, no new internal combustion engine car sales at all in the world. So, this is not far away. So just on electricity, here it's broken out in advanced economies and emerging market economies. Emerging and developing economies account for 75% of the projected global increase in electricity demand. And that's really driven by, the increase in population, but also you can see wedges appearing there in terms of transportation. So there's light green wedges, electric vehicles essentially, and then there's hydrogen supply. And similarly for the advanced economies, we've been quite flat with our electric use of electricity, but that is also set to increase as we move toward this higher electrification of our total energy system. So again, driven by the transportation sector, light vehicles, electric vehicles, and also generating what we call green hydrogen. So this will require, a complete overhaul of our global voltage transmission distribution systems, and lots of electric charging stations, and it will change the whole way that grid networks work. But electricity networks that have taken 130 years to build need to more than double in total length by 2040 and increase further. So this is a huge area of activity that is starting to happen and requires quite a lot of investment as well. Industry, we talk about, this is one of the harder sectors to decarbonize, and that's really because if you look at the breakdown here on the right, you can see that industrial emissions of about 8 gigatons of CO2, mostly coming from cement, iron and steel, and some other industry. And there are really no alternatives to iron and steel or cement at the moment. I mean, look around you, the buildings that and the infrastructure we have, it's all steel and cement. And steel, of course, requires high temperatures to melt iron ore and reduce that iron oxide into molten iron, and use the coking coal not only for that heat, but also as part of the constituent of the steel itself. So there's really very little alternative to using coal in the steel industry. I know there's a lot of great innovations now happening, and there's lots of headlines, but it's all still very early days, and we need to see how economic those are. So that's a difficult one. And similarly for cement. Cement basically takes limestone and heats it into very high temperatures of 1500 degrees Celsius, and that you cannot do through electricity really. So that is where coal has typically come in. So there need to be alternative solutions for that as well. These are difficult to decarbonize systems, and therefore will require some way of capturing the CO2 and putting it into the ground, and that's where carbon capture and storage can play a role. Also hydrogen can play a role in this sector. This is in terms of transportation we talked about already. You can see the top curve here, the sort of darker green, that's light duty vehicles. That's already happening. We see a lot of electric vehicles appearing on the roads. Nowhere near enough, of course. But that is happening, and every manufacturer seems to be now marketing their own electric vehicles. Heavy duty vehicles like trucks, a bit more difficult, and that's really because the weight, you need to reserve a lot of space in a truck for the freight, and the heavier it becomes, the heavier the weight of batteries you need to haul as well. So yeah, many companies are thinking that hydrogen fuel cells are maybe a better solution for the heavy trucks. So that really is linked very closely with hydrogen. And then there's of course aviation and shipping, which are less, they emit less, but equally need to play their role. So yeah, if you look at the graphs, you can see that by 2050, in terms of the fuel used in the transportation sector, very little fossil fuel, a large amount of electricity, some bioenergy, and hydrogen-based fuels. And yeah. And then buildings, finally, the last sector, they consume about a third of global energy and emit about 20% of the greenhouse gases. And this is a challenging part because this sector, it is, I read somewhere that there's about the equivalent floor space equivalent to the area of Paris being added every week in terms of building floor space. So there's a large amount of building going on, and that's of course, yeah, we can see that always all around us. But the good news is that today's cost-effective technologies and practices that already exist, they don't need to be developed or researched or new innovations. The ones that exist can result already in a 40% emissions reduction by 2030 and 95% by 2050. And this is based on studies from the International Energy Agency. There's also behavioral changes need to play a role. The two big things that play a role in decarbonizing buildings is really about energy efficiency, so becoming more efficient in how we use energy, and electrification. And you can see that on the waterfall chart at the bottom there. So although building will increase in terms of floor space, by making things like building codes that would require all new buildings to be either zero carbon ready or themselves already zero carbon, they can be ready for when zero carbon solutions such as electrification of heating already happens, or when there's more renewable energy available to create renewable electrification sources, then these buildings can also become zero carbon ready. And the long lifespans of buildings means that we really need to act very urgently and make sure those building codes are developed in order to make that happen. There's a lot of barriers to that, so that's definitely a challenging area to decarbonize. I'm aware of time. I'm running out. I'm going to just very quickly jump to a slide which I think is important. So we did talk about the electricity system becoming more reliant on solar and wind, and that means there's more intermittency. So this is the concept that we cannot always rely on sun and wind. It's dependent very much on the weather. So the electricity supply side is going to be fluctuating a lot more than we're currently used to. And we are used to having a reliable supply of electricity. So electricity storage is a big thing, and that's what this slide really talks about. There's various types of batteries around. There's a lot of innovation happening there. We're leading very much by Japan and Korea in terms of the patents. You can see that on the bottom right. You can see how a battery is typically made up here on the animation at the bottom there. So mostly electrolyte solutions, copper, aluminium, and plastic. But then the cathode is really where a lot of these exotic materials come into play, such as lithium, nickel, cobalt, manganese. And that's really going to lead us to we'll move from a fuel-intensive energy system to a material-intensive energy system. And I'm going to take this as the last slide. I have a lot more that I would like to cover, but I realize I'm running out of time. But I want to leave this message that, look, we are in this energy transition at the moment. And if you just look at transport, the top graph there, you can see an electric car requires 6 times more minerals than a conventional car. And I'm not talking about the aluminium and steel, but I'm talking about all the other components. And similarly, wind turbines use a lot more than a natural gas power station. So we are moving to a material intensive system, and that is going to give its own challenges in terms of supply chain and reliability of that, because there's 3 countries that really dominate most of the materials we need, and that's China, Australia, and the Democratic Republic of Congo. So we really need to do something about the diversification of that supply chain. So I'm going to leave it here. I realize I have a lot more that I could talk about. I'm just going to go to my main conclusions here, and some of them we will not have covered. So I will stop here and hand it back to you, Anastasis, and see if there's still time for questions.
Yeah, sure. There's always time for questions. It's just whether everybody else can stay back for them. There aren't too many questions that have come through during the talk. If anyone's got any questions, now's the time to put them forward. But as I said, you can send them through after the session by email. The first, not so much a question, but comment, just let me find it, was from Nicholas Taylor. And he was saying that, sorry, just let me find it, beg your pardon, that actually the historical correlation between CO2 and temperature seems quite weak. Now, I don't know if you've got any comments on that, Gijs.
I'm not sure it is really that weak. I mean, if you look at that graph of temperature, observations and the amount of CO2 in our atmosphere, we've gone from 280 to 415. We've not quite doubled. Double would be 560 ppm, and you can basically do the physical sums that and modeling that show, I think, our sensitivity, the planet's sensitivity to CO2 concentration, or CO2 equivalent, I should say, is about 3 degrees. So a doubling of CO2 concentration in the atmosphere leads to a 3-degree warming. So when you get to 560, we'll basically be 3 degrees warmer than and there's a bit of an uncertainty range around that, but I think there's very little doubt. I mean, the science is pretty unequivocal that there's a very clear link between CO2 and temperature increase. You can read all the IPCC documents. That is science that is by now pretty much undisputable, I would say.
Yeah, Nicholas also mentioned that he suggested that autonomous vehicles might make it easier to electrify freeway lanes for trucks and buses, in that they'll be able to control and coordinate lane discipline and weaving on the roads. I'm not familiar with that. Topic.
The transportation sector. I mean, I'm touching all of these things very briefly, but each one in themselves is a huge topic. And, you could argue, well, do we need? I mean, we all assume we need to own a car, and we all, is that really the model we need? There's lots of ways. There's lots of different ways of thinking about mobility, and that is also part of the solution, of course.
Well, I lived in London for 20 years, and I love London. Even though I live in Australia, I'd go back to London anytime. But I was there 20 years, and I didn't own a car, and I don't know if it's because London's unique and it's got a fantastic transportation system. But I think governments need to really think about the networks that they have and how they can make them more usable and more attractive to people to give up their cars, even if they are electric. They still contribute. You've still got to mine for minerals, etc., to build them. Okay. Eric Kai. The MI has already created several coalitions to combat energy transition. The MI being the Mission Innovation. I'm not sure if you mean that they're helping the energy transition or opposing it, Eric. I'm assuming it's to aid the transition. Mont, somebody I think you know.
Oh yeah. Hi, yeah.
It seems that what is needed in the intermediate is abandon coal first of all. I can't agree with more on that. There's a lot of resistance in Australia to abandoning coal, with our Prime Minister a couple of years ago holding it up in Parliament, professing its merits. Then oil, and increased use of gas until we have sufficient alternatives. And I totally agree with Yap. I know a lot of people don't agree with gas being used, but I think for a smooth transition, and there have to be plans in place to not just let gas linger on forever, but if we want it to be smooth and unchaotic, I totally agree with Yap there. We've got Nicholas.
I have one comment to make on that. So if I just make one, I think I agree with that as well. But of course, what we all need to do is just simply, a lot of energy gets wasted. So if we can reduce our use of it, our demand for energy, that also helps. And I think in that respect, one comment I would make, I'd always like to thank, President Putin for invading Ukraine, because Europe is now going through exactly that dilemma of, look, we now have, we are for the first time limited in our supply of energy through gas being cut off from Russia. And so Europe is having to make choices. Do we keep a factory open or do we keep a hospital open? And it's going to be very interesting this winter, because I think those choices in Europe are, what we're all going to be facing in the future as energy becomes more expensive and less surplus, because we have been living in surplus, and that's not going to be the future case. So we all need to make choices in using energy smarter, in addition to moving through this transition.
I actually totally agree with you there, and that trumps what I just said. And I think what Yap said, it is energy conservation, and we went through a big period of that during the energy crisis in the 70s. And it's just things like, in the winter, put an extra jumper on. In the summer, try and stay somewhere cool. Don't use your car as much. And if you've got children like I do, you have to follow them around and turn all the lights off in the house and the fans. And you know,
For me, the
it's just,
classic one is a dryer. You know, many people have a dryer.
yeah,
We actually don't have one here in the apartment I'm living in. But you know, if you wash your clothes and then you put them in a dryer, the dryer turns and dries your clothes and consumes electricity. Whereas, you know, usually there's either sun or there's wind outside. If you hang it up, you don't, you know, you immediately are using a renewable resource rather
yeah,
than having to build a wind turbine or a solar panel. You know,
yeah.
so there's lots of these examples where you say, well, actually, that is just a luxury we can do without.
Yeah, I think we underestimate as individuals what impact we can have on this transition just from little
Yeah, that's
actions
right.
like that, and not waiting on the governments to actually do things.
I agree. Yeah.
Yeah, Nicholas Taylor, I'm
Yeah.
just reading his comment out here. I don't doubt sensitivity, other things being equal, some questions whether CO2 or temperature comes first when change is slow, e.g. in ice ages. Yeah.
Well, I mean, yeah, that's a whole debate. You know, what comes first? If it was temperature warming first causing a CO2 increase, I'm not sure exactly what the science of that would look like. But
Yeah.
yeah,
And
I mean,
Eric, sorry.
yeah, there are issues around. I mean, ice ages is a bit different because those are related to changes in the Earth's orbit axis. You know, these Milankovitch cycles. So yeah, those are a bit different. But yeah, anyway, there's a whole climatological debate there you could have.
Yeah, sure.
Probably not time for.
Eric's provided a link to the Mission Innovation. It's www.missioninnovation.net. The main intergovernmental platform, everyone can see that, so they can read that because there's a fair bit there. And Yap has commented again. Thanks for joining us, Yap. I was hoping Bert would join us as well. One reason China doesn't look good is that we have exported part of the CO2 producing industry to China. It's a good point. They make things cheaper. That's why we've done it instead of manufacturing things ourselves. In addition, the CO2 should be considered per person. Good point. Yeah.
So this is one of the reasons why Europe is now also, as part of its update, NDC is introducing this carbon border mechanism, so that we are no longer. I mean, indeed, we are exporting our emissions by having heavy industry manufacture things outside Europe, and that shouldn't be the case. Yeah.
Yeah, that's an interesting point because Australia, our government was talking about, well, when the coal leaves our country, it's got nothing to do with us and it doesn't count to our carbon footprint. Yeah. But there's some snakes in our government, that's for sure. Yeah, and Nicholas, we take, you're just playing devil's advocate. That's all right. Thank you.
Yeah.
Any other questions? If not, I won't wrap it up quickly, but I'll give you a minute or two. But thanks, Gijs, for the talk. And if anybody is interested in going into this in more detail, we're available to organise that for you or for your organisations, because it is an area.
I have a much more detailed course that which this is a carbon extract, and you can see I already ran out of time. There's lots more to talk about in this whole area, so I'm very happy to do a training course.
Yep. Okay. Nyaps asked the question: how about Scope 3? How to have that done? So.
Yeah. I don't know if everyone understands that Scope 1, 2, and 3. I mean, that's another slide which I didn't include. But that's around the whole carbon accounting, how organizations can start to reduce.
I'm sorry, you've frozen there.
Emissions. You first of all need to have a really good one come in.
Yeah.
Oh, okay.
Yeah. Oh. That's all right. You're good. It's an interesting. It's been a good talk. There are a lot of challenges for us, for the world, and the future. There's no doubt about that. It'll be interesting to see how it plays out.
Okay. Well, thanks everyone for listening. It's always good to have an audience for this kind of thing, and I hope that I've left some good messages behind, and that you all can use that to trigger further conversations in your own communities around how to help move this forward faster, because that's what the world needs.
Yeah. Okay. Great. Thank you. All right. I'll hang back for a minute or so in case anybody's any questions or wants to talk to me about doing anything further. But thanks.
Okay.
And we look forward to seeing you next week for our SURF, subsea umbilicals, risers and flow lines. Okay. And lots of thanks coming through for the talk.
Okay, great.
Cheers.
I just made a little comment. Feel free to reach out to me through LinkedIn.
Yep.
All
sure.
right, I'm going to dial off. Thanks very much, everybody.
Thank you.
And thanks, Anastasius, for moderating.
Cheers. You're welcome.